This is all about solving systems of linear equations even in a case when the equations are not compatible, and even in the cases if our matrix is not square, we can have more equations than unknowns, even conflicting equations, or we can have less equations than unknowns, when of course you can't really find a unique solution, but the least squares approach always give you a solution, but of course it is in cases when there is no solution in the classical sense. Of course, this is something a little bit different that the least squares computes, and it is highly useful what it does. So let's consider systems of linear equations and least squares solutions. First case, two equations, unique solution. So let's start something that works nicely and there will be no problems whatsoever. Let's first take equation 1, for example, y equals x, a very simple linear equation. And let's take another one, equation 2. We have, let's say, y equals, let's say, 2x plus 3, something like this. As always, it's a good habit in Matlab and computational science, plot everything. When you work, just keep plotting, plot, plot your functions, plot your images, everything, to keep track that you're doing what you think you're doing. It's very easy to see some problems up here when you can visualize them. At least that's the way I work, and many of my colleagues. I highly recommend. So let's take a look. And in Matlab, usually I like to open a window, clear it. This is clear figure because we will anyway run this file many times over and over. So we clear the previous ones, and let's actually do it like this. Let's make a set of evaluation points, for example, from -2 to 2 and maybe 500 points. Well, actually, these are linear equations, so we only need very few. Even 2 points would be enough, but let's have 5 for the heck of it. And so then let's plot the first equation. We plot this x plot, and then we have our y just equals x. So actually it's this one, and let's plot it in blue. Let's see what happens when I run this. All right, we have our linear equation there, or the graph of the linear function we are looking at. And then we need to put hold on so that the previous plot stays, and we plot another one in the same picture. Second equation, and that was, what was it? So we have 2x plus 3. Let's plot it with red. and see what happens. This should be xplot. Briefly there I was wondering, why is the linear function so non-linear? Okay, so we are starting to get an idea where the solution could be. I'm not plotting far enough to the left side direction, and also you can't really see what are these points, so let's make them more visible. This is also a little lesson in visualization. Whenever you're showing something on the screen, in your talks or whenever, it's one of the good principles. Make sure that what you want to show can be seen. I know this sounds like something coming out of an airport book, and well, yeah, it could. But anyway, trust me, it's a good advice. So let's write here parameters for plots, and let me choose a width for the lines. Let's take that one, and then font size, let's say 16, and let's see what happens. So here I'll add here, I think we will get a little bit thicker lines to show the functions, and then yep. Sorry? Yeah. Oh, it's because y equals x. So xplot is a discretization of this guy, and then we see what in the equation, what is the y coordinate. In this case, it is the same. So I could write it like this. Maybe this is more clear. Does it make more sense this way? Maybe? Well, anyway, when plotting with the plot command, we have some x coordinates, and then we have the corresponding function values. Here is evaluate the function we want to plot. That's the thing here. But now, actually, I think we are not plotting for negative enough argument points, so let's make that one, and also maybe let's put it this way: xmin is -5, xmax is, let's say, 2. So here xmin, xmax, and we could here, I'll take get current axis, and then I put the tick marks to the plot, let's say from xmin to xmax, and then I put the font. Like this. So let's see what happens now.
You have an extra minus mark then.
Where? Ah, true. Huh. No wonder it looked weird. So this is much better. Although I don't know if, probably you still cannot see these numbers. So let's put the font size up to 30. Maybe not enough. Let's put to 50. Okay. Can you see these now? And the line width, maybe it's too little. Let's put more. Okay. Can you see this in the back now? Okay, good. All right, so we have two linear equations, and the solution, of course, is the one unique pair of x and y values that satisfy, that lie on both of these graphs, and we can see that point in the crossing of these two paths. So now let's move on to solving our equations. So that was just taking a look at the functions. So here is a matrix solution. So we have an A matrix. So for the first equation, I think we should have, let's see, 1, 0, and then 2, 1. Right hand side is 0. Sorry, I think it has to be -2. Because here, if I put it so the equation would be -x plus y equals 0. And here we have -2 times x plus y equals 3. So from these two, when I pick out so I think our matrix, okay, so we have -1, +1, they are here. Then we should have -2, +1, they are there. And we should have on the right hand side 0 and 3. Like this, I hope. And then our solution will be x equals the inverse of A times B. And here plot the unique solution here. So we plot or maybe let's call this the result, because then x equals the first element in the result and y equals the second element in the 2 vector that we get out of our solution. So then we plot the solution. So this would be x, y, and it's only 1 point. So I will plot it as a black point only, and there I will put the marker size to be big enough. So we need to have here something to make the marker big. Let's see what 15 would do for us. Okay, let me plot this and let's see what happens. Okay, I think our marker is still too small. Let's make the marker bigger. Maybe even bigger. Okay, so here we have a visualization of the 2 equations we are solving, and a picture of the unique solution. Then, as our first example of let me just copy and paste the whole thing first, and then we have second case. two equations, no solution. And in this case, let's put equation 2 equals y equals x plus 3. So I think y cannot really equal x and x plus 3 at the same time. Let's write this matrix is this one, and you can see this is a singular matrix. The determinant will be 0, so we can't really solve this one. And let me just quickly comment these ones, and let's comment this one as well, and just see how it looks like in the plot. And let's make this actually figure number 2. So I just run the section. Okay, so now, why is this so small? Let's run it. That's strange. But anyway, so now you see we have two parallel lines, and to solve this pair of equations, we would have to find a point in the plane that belongs to both of these lines. As you know, there is no such point. There is no solution for this set of equations. Nevertheless, we can use least squares solution here. A is not invertible, so there is no inverse for A, but we can use the backslash operator, also known as könökeppi. And let's see what happens. Okay. Nothing happened. So let's do actually, instead of könökeppi, let's do pseudo-inverse of A. Not inverse, but pseudo-inverse. Where is our solution? Come on. Oh, I didn't plot it. I commented it. Okay, so there is no actual solution to the pair of equations we are considering. However, the least squares methodology will find kind of the best possible solution. It will, first of all, it will look for points that are as close as possible to both of these lines simultaneously. In the first case, it's absolutely clear. I mean, the unique point that's as close as possible to both lines at the same time is the point of intersection. There, the distance to both of the lines is 0, and one cannot do any better than that. In this case, actually, there is an infinite number of points in the plane that are at equal distance from both of those lines. I think you can probably guess what it is. It's the line that has the same direction than these red and blue lines, and it's going exactly halfway between those two. Any of those points on the line exactly halfway of those is kind of satisfying both of those equations as well as possible simultaneously. So then the minimum norm solution computed by the pseudo-inverse picks out the shortest vector out of these infinite possibilities that are simultaneously as close as possible to solving both equations. But this is what happens here, and this, yeah, question. Why did it plot right there? What I didn't hear the rest. This solution. Okay, so what happened here? let's plot let's put here one extra line, plot plot all least square solutions. I think, let's see. I think this will do the trick. Let's see what happens. To put it briefly, I want circles to stay circles and not ellipses. I don't want the plot to stretch in any way, so I will put here axis equal okay. So this is our situation. We want to find points that lie on the red and blue lines simultaneously. There are no such points in the plane. However, there's an infinite number of points in the plane that have an equal distance to both of those lines, which we, in the least square sense, they are kind of as good solutions as we can get. They are kind of closest possible to solving both of the equations simultaneously. So that's the thin black line in the middle. And then we still want to pick a unique answer to our problem. We want to find one best possible solution to this unsolvable problem of two equations. So then we pick out of those points on the thin black line, we pick out the vector that is the shortest. That's how the black point there is picked.